Okay, so we have, we're continuing 1.3 right now. These ones are going to be just a little bit more involved than the ones we looked at in the last video. Okay, in this case, the degrees aren't as explicit with these rational functions. So we just have to think about what they would be. Okay, so for example, the degree in the numerator of example A is 1. The degree in the denominator appears to be 2, but we have the square root of that. Remember, square root is the half power. So half of 2 is 1. So we actually have the same degree in the numerator and the denominator. Now we just analyze the sign. So the top will be positive and the bottom will also be positive. So we get 4 over square root of 9, which is the root. And we have this time, if we plug in negative infinity, at the top we're going to get negative 4. In the bottom we're going to get positive because it would be squared. We take the square root. So we get negative 4/3 for our end behavior. So that would be horizontal asymptotes for this graph at y equals plus or minus 4/3. Okay, the next example. Let's see, I'll take how it's for limit as x approaches infinity g of x. The top, the numerator power is 3. The bottom, it's technically also 3. So we are growing at the same rate at the top, same rate at the bottom. So if we put a positive infinity in the top, we get a negative 2. Positive infinity in the bottom, we get a square root of 11. You can rationalize that if you want or not. You can just leave it. Limit as x approaches negative infinity. This time in the numerator, negative, negative, negative. That makes it negative, but we have that negative 2 in the front. So we have to put a positive. The bottom's always positive because it's a even power. So we have in this case horizontal asymptotes at y equals plus or minus 2 over square root of 11. So it seems that that's always the case, right? Not true. All right. In the top, we have a degree of 2. In the bottom, we have a degree of 3. So the bottom's actually growing faster than the top is. So if you remember in that case, if the bottom grows faster, it's approaching 0. Okay, it doesn't matter what the signs, because we don't get 0 with sign. So in this case, we have a horizontal asymptote at y equals 0. All right, so we have some bonus problems for these limits at infinity. The degrees are easy, okay, because it's just the same kind of function. You're just comparing the degrees, but not all functions are simple as that. So if we have a constant, that's probably the slowest, right? Because it's not really growing much at all. If we have logs, they're the next slowest. Then anything in this form, okay, anything in an exponential form, okay, polynomial, exponential. Okay, if you remember what that is, factorial. It multiplies anything before it. And then we have the king of growth here, x to the x. So if you remember how fast they grow, we can compare the problems. Okay, so for example, we have this polynomial function in the top. We have an exponential function in the bottom. Now in this case, exponentials grow faster. So the limit as x approaches infinity is 0. Okay, part B, the numerator is a constant. It's not growing, it's not changing, even though it's a really big number. This bottom part is going to grow faster. So again, 0. Okay, we have a log function in the numerator, and we have a polynomial function, x to the 1/9. In the denominator, that seems pretty small. It doesn't seem like it's going to grow very fast, but it still grows faster as we go to infinity than the numerator. So again, another 0. Okay, then we have an exponential function and an exponential growth. The bottom one is growing faster. Okay, then we have this factorial, the growth again, 0. Wonder if they'll all be 0. Here we have the king of growth than the factorial. So the top, the numerator, is growing infinitely faster than the denominator. So this one is, in fact, infinity. Okay, last two problems, and this one will be for your whisk. You can write it right in the summary. Okay, this function has to let x get very, very large. So e greater than minus 32, something really, really big. Okay, over 4 plus 3 to something really, really big. This 8 is not really going to make a big difference to us. Because we're going to be subtracting a very large number. And this 4 isn't really going to make a difference to us. They're adding this really, really big number. And notice that the growth rates are the same. So we're going to get negative this number, or positive this number. So that ends up giving us a ratio of negative 1 over 1, or just negative 1. Okay, so for part B, I'd like you to analyze this one and be careful because you're going as x approaches negative infinity.